Hi students, in today's video we are going to be talking about an important topic relating to data science and machine learning, which is overfitting and underfitting. This is important and becomes very important in the context of large language models, where we often hear that hallucination is caused by overfitting. So it's important to just have a sort of theoretical, an intuitive idea of what is overfitting. So let's get to it. All right. So essentially, when we suppose what is overfitting intuitively. Now observe over here. I have three different. I have some data, and I have three different models which have been fitted on them. Now the first model, as you can see, in no way captures the straight line. In no way captures most of the data points. This particular model would be a terrible model to use for prediction. In the third model, on the other hand, literally every twist and turn and every little blip in the data is sort of incorporated in some fashion in the model. Again, this model may not be good for prediction simply because, it's unlikely that the fresh data will mirror the patterns that have been observed earlier. So, again, it is not going to be a very good generalizer. The model in the middle seems to be a good fit robust model. It broadly follows the main trends in the data, but at the same time, it doesn't follow every little blip that is there. One question you might ask is, how do you get such an overfitted model? Now, overfitting can be done through a variety of ways, but primarily amongst them, the first way is basically having a model with a very huge number of variables. So that can definitely lead to overfitting. The second approach might be to also have a model where for example the model is actually undergone lots of polynomial transformations. So for example, instead of x you use x squared or x cubed or x to the power 5. Again, these such models using a mathematical function such as that can lead to a very overfitted model. How would you identify an overfitted model? One of the key signs is a very high, very low test error, and so that means a great R squared, and a very high test error on test data, very poor quality predictions. So, coming to the point that this is one of the major reasons to avoid overfitting. We actually, in any data science modeling process, we normally do split our data into a training set and a test set. The training set accounts for 70% of the observations, since you want the bulk to go into estimating your algorithm, and the remaining 30% is split with 15-15 into the validation and test set. Now, the validation set is basically this set where you are actually experimenting by varying what are called the hyperparameters of the model. Loosely, in the context of regression, this might just be something as simple as the polynomial form of the equation. So, you might try a model which is x squared, x cubed, x to the power 5, etc. Now, each of these models is, you would estimate them on the you would test them out on the validation data set. Now, because so much of fine tuning has taken place on the validation data set, it is not completely independent of the algorithms trained on it, and therefore it's not a good idea to test on it. Hence, the test set is completely fresh, completely untouched data, which is then used only for validating how well this final algorithm works. A related point is what are learning curves and overfitting. So as you can see over here on the left hand side, I have three different models which have been fitted to data. There is a straight line which is orange, a green one which is a blue one which is your overfitted model, and then a more optimized green one. Now, learning curves essentially enable a means by which in data science, we use them to actually understand model selection and to see how your mean square error changes with changes in the different types of models which are being tested. Now, on the x-axis, for example, we are charting flexibility of the model. Loosely, again, in terms of the context of regression, this is about how, what is the level of polynomial transformations that we have used. For example, is it x squared, x to the power 5, x to the power 10, etc. On the y-axis, we plot the mean square error. Now observe that for the overfitted algorithm, we see that the test mean square error declines consistently as we increase the complexity of the algorithm. And that is to be expected. As we develop more and more complicated algorithms and more mathematically complicated functions to capture all the variability in the data, obviously your training set data error is going to go down. However, observe the test set data. Test set mean square error. Initially, as the model complexity improves, you do see a decline in MSE, and then after some time it starts to go up as the model becomes too complicated and does not generalize well. So these are the classic learning curves which are very often, especially in the case of neural networks, used to select the most optimal model which offers the lowest MSE. Also, on a related point, let's talk about the bias and variance trade-off. Now, essentially, we can think of bias and variance in the following way. When we talk about fitting a model, I think these dartboard bullseyes illustrated quite well. Now, let's look at the top row, which is basically low variance and high variance. What is low variance data? Low variance data is data which is very highly clustered together around the central target or bullseye. So that's low variance, it's clustered together. High variance data is data which is sort of spread out around the bullseye. Now, variance is essentially the inherent variability in the data. The second thing is bias. What is bias? Bias is basically when we have estimated a model which is not really in any way correct related to the data. In this context, for example, it means that even in the low variance case, all the data is clustered quite far away from the central bullseye. And even in the high variance case, the data is quite far away. Now, typically, what do we mean by a high bias, low variance model? Typically, it means something along the lines of this, a straight line which in no way captures the inherent data structure and variability of the data. So, to avoid this, can we, data is the new oil, so can we actually just add on more data? Well, no. Adding more data points to to bias does not help. If your inherent model is not correct, it is not going to improve by adding more data points. It will continue to be biased. Therefore, if you have a biased model, the best thing to do is to add some complexity to it and to start making it more relevant in some way by fine-tuning or by adding mathematical transformations such as polynomials, etc. Now, on the other hand, what is variance? Variance, as I said, is the inherent variability in the data. Now, how would it help in the case of high variability to add on more data? In this case, yes, because a smaller data set essentially means that the algorithm is often translating data points which represent noise into a core part of the algorithm. As we add on more data points, the algorithm is able to downplay the importance of noise elements, and therefore capture a far better aspect of the true data model. So yes, in the case of variance, it does help to add on more data. In the case of bias, you have to work on the model and improve it. I hope you like this video. So I'll see you in the next one.